Good morning, everyone. So I welcome you to the third lecture, and the topic is microgrid architecture and control. So the philosophy behind this lecture is that when you talk about a distribution system, nowadays modern distribution system are becoming isolated systems. For example, let's say you take about any institute, whether it is IIT Dhanbad or any other institute near around from where you are coming, we all have backup diesel generators, and whenever there is a grid disconnectivity, our own generation, local generation comes up. So to meet the local distribution system demand. And in addition to that, we also have renewable energy sources. Like nowadays, government is putting so much focus on putting rooftop solars. So let's say we have rooftop solar now, and we have to integrate in our campus distribution system. So basically, this small geographical region, which is now a small electrical power system, because as you know, a power system is basically a synchronized interconnection of generation, transmission, distribution, loads, all those things. Now the similar concept is there in a distribution system where you have your own local generation, then you have loads, you have your distribution feeders, laterals and all. So the distribution system itself may behave like a small grid, and that small is how small depends on the power rating. So you know, usually when we talk about the grid, we talk about gigawatt scale grid. When you talk about a distribution system grid, it will come down to small power, like maybe kilowatts, some megawatts, few megawatts. So therefore you can have microgrid, mini grid. The concept is that whatever is the size of it, it will have its own generation, which is not there in the classical power system. Because you know, inherently the power system is designed to have a generation, transmission, distribution and consumption approach. But now with the integration of distributed generation, most of these distributed generation are renewable energy generation. So the distribution system actually now have the capability to generate power. Okay, so the geographical area which has the capability to generate power and consume power, we call it a microgrid. And the microgrid has the feature that it can be connected to the grid or it can be disconnected to the grid. So the microgrid can be a grid connected microgrid or it can be a islanded microgrid. Alright. So by definition, the microgrid is an integrated energy system just like a conventional grid. It will have its own control, communication, sources, loads. So it's an interconnection of loads and energy sources. We use the word distributed many a times because the classical generators are located at a central point. For example, large bulk thermal power plants or hydropower plants. But the distributed generators, the local generators are distributed. Like you can have rooftop on one building, rooftop of another building, rooftop on another building. So the generators or the energy storage or the energy sources are distributed in nature, and that is why we call them distributed energy resources. So when you have an integration of distributed energy resources and loads making a microgrid, it can be connected to the grid or it can work as a islanded. Now the objective of microgrid is to have energy reliability, security and efficiency. The most important point is to have reliable power supply, because if let's say there is no grid available due to some natural effects, for example, let's say it's thunderstorm or all, the grid is not available or whatever be the reason, if the grid is not there and you have to give supply, now what you do, you have your local generation. So you improve the reliability of the system and you meet the sources, loads for a longer duration. So that reliability is basically improved. And then we say it's more efficient because you have your local generation, local consumption, so the transmission or distribution losses are reduced because you don't have to send power through long feeders. Alright, so it's an efficient way of giving energy supply to the loads. You have to understand the microgrid like a conventional grid, only the difference is the size. So it should have its own proper control capabilities. control and regulation. It should not happen that if it is a very small size of thing, you should not think that it can operate randomly. No, even if it's a microgrid, although it's of a small size, the frequency, voltage, active power, reactive power, whatever your variables are, they have to be properly controlled, coordinated. All right. So a microgrid is developed with the objective is to provide sufficient and continuous energy to a significant portion of the internal demand, or basically the local demand. It has its own internal control and optimization strategy that is very important. And in this today's 2 lectures that we have now, we will discuss a lot about the control strategies that are used for microgrids. Then the flexibility is important because you have the generation with you, you have the loads with you, so it gives you a flexibility of control. You can control the loads, turn on, turn off, you can control the generation as well because the generation is with you also. In a traditional power plant, conventional power system, you cannot control the generation, right? So that is important, okay? The microgrids would invariably will have a storage, because the generator which are there in the microgrids are usually renewable based generation like rooftop solar in most cases, and there is always a variability associated with rooftop solar. So therefore it is important to have storage, alright. And microgrids are available in various sizes, ratings starting from few volts or few watts, kilowatts, sometimes some very small gigawatt level also, okay. So a microgrid provides multiple benefits. It provides economic benefits because you have sources which are of different operating costs, and you can earn money by sending power to the grid. For example, in the evening peak time, the microgrid can give power to the grid, and then you can earn money like that. And then it is more economic because there are less number of T&D losses because the distribution is very small. You have the local generation, local consumption. Okay. Environment benefits because most of the generators are renewable based generators, therefore you provide environment benefits. Then the microgrid also provides some technical benefits in terms of peak load shaving, reliability enhancement, grid support, like that. For example, let's say you all know there is always a peak, evening peak, and in a day we have 2 peaks, the evening peak is always higher. If you have a local microgrid with, let's say, storage or local generation, what you can do, you can transfer power to the grid in the evening time, in the peak time, and you can earn money. So like that you can support the grid, so the peak demand of the grid can be reduced, you can earn money, so it's a win-win situation for both. You earn money and the grid also is happy because the peak is reduced. So the whole point is the microgrid brings a lot of benefits, and we have to understand how the microgrid operates, okay. The microgrids are of different sizes, as I told you, depending on how much is the power supplied. Okay, it can be just a few, like a very small building, a campus, or a multiple campuses. So the concept is, for example, let's say a small building which is a important building like a hospital, where you need a continuous and reliable power supply. You can make it as a microgrid. You can make this campus as a microgrid. And if you merge multiple areas, multiple buildings together, then it becomes a community microgrid. All right. Technically, if you talk, the classification can be either AC, DC, or hybrid microgrid. So most of the energy transmission that we have is in the form of AC. But now we are talking a lot about DC as well. So DC microgrids have their own benefits compared to the AC microgrid. Why? Mainly because your generation and loads are mostly DC in nature. For example, when you talk about renewable, your solar is DC. Correct? Your loads, when you talk about, for example, nowadays we have battery based like EVs, laptops, mobile phones, they all are DC because they need, at the end of the day, they need DC power. So if you have a DC network, you reduce the number of conversion stages from AC to DC and back to DC. You can directly use DC, right? So therefore, DC microgrids are coming up a lot when you talk about the upcoming structures. For example, let's say a rural area which is not electrified, because you cannot change what is there, but the things which are now coming up, for those areas, what you can do, you can put up DC microgrids. Now, somewhere we already have AC microgrid, somewhere we can put DC microgrid, and there is a concept called hybrid microgrid where together DC and AC systems can operate together. Alright. So immaterial of that, whatever is the type of microgrid, whether it is AC or DC, it is very important to have a proper control of the microgrid, just like a proper control of the conventional grid, right? So when you talk about a conventional grid, you know what you need. Obviously you need generation, transmission, distribution and loads, the electrical part that is always there. But then there is a control system, there is a communication system, right? Because your measurements, field measurements, for example, from PMUs, let's say, they are sent to the SCADA master station, let's say. So you need communication. So like that, you have control system, communication system, protection system, all those things are there in a conventional power system. The same thing has to be replicated in a microgrid. So the microgrid architecture can be kind of divided into three main components: the physical system, the control system and the communication system. The physical system includes all the physical power system components that you can think of. Right? What do you think in electrical system they are? You can think of generation, loads, your power electronic devices, your switches, your protection equipment, relays, circuit breaker, fuse, whatever, measurements, right? Energy meters, smart meters, those things are your physical system. Then your control system is important. Just like for a conventional power system, you have to control the frequency, voltage, active power, reactive power, these variables, like power factor, harmonics has to be within a limit, so everything has to be properly controlled. And how do you achieve that control? That is done with the help of a communication system, because at the end of the day you will have field devices, and those field devices will, with the help of certain sensors, will give you some measurements. In our system we can say those measurements would be voltages and currents, and then what you derive from these voltages and currents is a different story. So those measurements of voltages and currents are then sent to a control center, where the control center takes a decision, and again the command goes back to the field devices and some action has to be taken. So the communication system plays a very important role. Alright. So the whole point is this microgrid will have its own devices, its control system, communication system. And now when you talk about the control system of a microgrid, this is the focus of this lecture today. The microgrid control, when we talk as a microgrid control, a microgrid contains many things. So we mainly talk about the control of the energy systems or the energy sources. For example, let's say a rooftop solar, okay, or battery energy storage. So like those things that are there, so the control of those sources is what we mainly focus when we talk about the control of the microgrid. Now, control of the sources, you cannot control like them directly. That means take for example, let's say you have a rooftop solar and you put the rooftop solar, the panel is fixed. You cannot do anything with the panel. At best what you can do, you can have a mechanical tracker to track the sun and all those things, but as such, other than that, you cannot do anything with the actual generator like this. What you do actually, you control the interfacing converters. So this is a big difference between a classical power plant, like a thermal power plant, where you control the steam valve or those things to change the generation. Here what we do, here we change the interfacing converter. So that is why when you talk about renewable energy sources, invariably all the renewable energy or the distributed energy sources will have a power electronic converter connected to it. So you must be doing some simulation, some project work that you may be doing, carrying out. All the renewable energy sources, distributed energy sources will have some kind of power electronics associated with it. Why? Because the power electronic device is something that we can control, right? For example, if you have to control any home appliance, what do? We let's say change the voltage impressed across this or something like that. Now, one thing is that we go to the old era using rheostat, potentiometers, we divide the voltage and use those approaches. Or the better approach is use power electronics. You have buck converter, boost converters, you have inverters, so you can play with the voltages the way you want. Alright. Once you can play with the voltage, you can get the desired result, what exactly you want. Okay. So like that, by controlling the power electronic converters, we control the electrical variables associated with the generators that are in the microgrid, and that is how we control the microgrid. So the focus now completely shifts to the control of the power electronic converters that are there in the microgrid. Now, there could be DC microgrid, there could be AC microgrid. If it is a DC microgrid, the power electronic converter is basically the DC-DC converter, the buck converter or the boost converter. And if it is a AC microgrid, the power electric converter is the inverter. Alright. Now we will develop some concepts in this lecture around the inverter for the AC microgrid, and we will extend the same to DC microgrid. So the concepts can be replicated as it is. So no need to repeat the same concept. So because most of the electrical power systems are still AC systems, that's why we put the focus on the AC microgrid, and that means we put the focus on the inverters. So now our focus is to how we can control an inverter. And very well you know from your basics of power electronics, to control a PWM inverter, what you do exactly, you do the PWM switching. And the PWM switching is done on the basis of one high frequency carrier and a fundamental frequency reference signal, right? Now, how do you generate that fundamental frequency reference signal that will define how your PWM signals will look like? Yes or no? And those PWM signals will decide when your power electronic switch that is there in the converter will be turned on and will be turned off. Correct? When the device turns on and off, you're based on the duty or the period when it turns on or off, accordingly your output voltage of that converter would change. Yes? So it all boils down to the generation of that reference signal which is used to give to the PWM generator. Alright? Now question comes, how do we know what should be the reference signal? So for example, let's say you know that the reference signal looks like this, a sinusoidal. Correct? But what should be its amplitude? Should it have a peak of 1? Should it have a peak of 0.5? Should it have a peak of 0.7? That decision has to be taken. And that decision is derived from what exactly we want to do. For example, if I ask you very simple straightforward question, if you have a rooftop solar photovoltaic, what do we want from it? You must have heard the term MPPT, that we want to extract the maximum power. Alright? So our objective immediately shifts to extraction of the maximum power. But how can we do it? The only thing is that is in our control is this guy. At the end of the day, PWM will be generated based on this reference. Our objective is to extract the maximum power. So how do we shift from maximum power objective to the generation of the reference signal? That control has to be mathematically developed. So first we have to define the objectives of the control. Correct? To understand that thing, there are two main objectives. So if you see here, an inverter can operate in two modes. One is called a grid connected mode, one is called a autonomous mode, or we say grid following mode and grid forming mode. So the grid following one or the grid connected one is the one which follows the grid. That means it has to be get synchronized with the grid. For example, you take it like this. You all have read a single machine infinite bus system. We say when there is an infinite bus, a single machine doesn't have the active and reactive power capabilities to change the voltage of the voltage or frequency of the grid. Yes? So what do we say then? Whatever is the power injected, whether it is active power and reactive power, it is injected while the voltage is fixed by the grid. So to change the active and reactive power, basically the current gets changed. Yes? That is the concept of a grid following inverter, that it injects P and Q, active and reactive power, but it follows the grid voltage. So that's why the name is grid following, that it has to always follow the grid voltage. It doesn't have the capability. For example, if I have a, let's say this building, I put a rooftop solar photovoltaic and I connect to the grid. The grid is of infinite size, cannot change the voltage, right? So it's the grid following one. But the other side of the picture is, let's say when the grid is out, for example, And let's say now we have a solar photovoltaic on the roof of this building, and we have to illuminate, or we have to give power to the building, fans, lights, all those things. Now there is no grid, so there is no other guy in the system to regulate the voltage. Now what do we want? We want a regulated voltage to be supplied to these equipment. For example, light, fan, they all want a regulated voltage. For example, here we have 230 volts AC, right? So that regulation of the voltage now is the responsibility of the inverter. So while we just talked about when it's connected to the grid, it is like a current source injecting a current to change the P and Q. Now it will behave like a voltage source to regulate the voltage in the to supply to the load. That is called grid forming mode. The inverter forms the grid. The inverter forms the necessary voltage that has to be there in the system. So that is the difference between grid following mode and grid forming mode. The control is nearly the same. There are slight differences. We'll discuss this in this lecture. So when you talk about the when you talk about this control, just a second. So when you talk about the control of inverter is usually done in the DQ axis, not the ABC frame. We all know. Let's talk about a three-phase system. You have VA, VB, VC, like that. You have IA, IB, IC. We don't do the control in the three-phase domain. We usually do the control in D and Q axis domain. So we use a transformation which is called a Parkes transformation, and we convert AC variables to constant quantities. Okay. So we have two axes now, D and Q axis, which contains the required information of the AC. The information is not lost, otherwise we won't know how much is the AC power or AC reactive or active power like that. The information is not lost, we just convert the three-phase time varying quantities to two-phase DC quantities. Why do we do so? Because the control that we all know is the best control for controlling real systems is basically a PI controller. And you know what is the transfer function of a PI control is Kp plus Ki by S. So you know that the transfer expression is basically Kp plus Ki by S. Now for a DC system, you know S equal to 0 basically. S equal to j omega. S equal to j omega, omega is 0. So if you put 0, you get a very high gain. So basically it's a high gain controller. And you know when there is a high gain controller, your steady state error becomes 0. So that is the purpose of converting three-phase quantities to DC quantities, so as to get the so as to make us enable to use the PI controller with it. So otherwise, if we use this PI controller with AC quantities, let's say I ask you to regulate a voltage, something like this. So instant by instant, your reference voltage is changing and having a certain frequency, which is your 50 Hertz, right? So the PI controller in that case will not work properly. The tuning will become difficult, because in that case you have to put this S as J 2 pi 50, right? It's not an infinite gain. So it's not guaranteed that a steady state error will become 0 or not. So that is why we do a Parkes transformation, and Parkes transformation is done using these matrices. Now there are multiple approaches to do the Parkes transformation because it's just a mathematical tool. So either you can say D axis leads the Q axis, or you can say Q axis leads the D axis, or you can say my D axis voltage should be equal to the peak of the phase voltage, or you can say my voltage should be equal to the RMS voltage, or you can say phase voltage, line to line voltage. Because you see, for example, if I ask you 440 volt 3 phase AC, in this what are the constant numbers? The line to line voltage RMS is constant, the line to line peak is constant, the phase RMS is constant, the phase peak is constant, right? So these are constant numbers. We have to extract those constant numbers basically, and we have to make sure that the peak or the RMS value remains at that constant number. That is the objective of the control, right? So which variable we are taking is our choice. It's just a mathematical number, and that is why if you read books, you may find different forms of the same expression of the same concepts. For example, here in this slide I have put two such formulas. the difference you see here is root 2 by root 3 and here is 2 by 3. But the concept is same. You convert the 3-phase quantities to DC quantities. Now when you convert the 3-phase quantities to DC quantities, you need this transformation matrix with your Parkes transformation. You need a variable theta. What is this theta? This theta is the reference angle and it has to be provided. So in a grid connected mode or a grid following mode, what we do is we use a phase lock loop, a PLL, and what we do is we convert the ABC to DQ. Now you can convert voltages, currents, all the 3-phase quantities to DQ quantities, but we start with the voltage because at a given point the voltage is regulated. For example, here in our wall sockets, what do we get? A fixed voltage, and the current would depend on the load that we connect. So current is the variable, voltage is the constant. Voltage is the point of coupling. Wherever we connect is called a point of common coupling. Yes? Okay. So the voltage is fixed, and that is why we take the voltage and convert it to dq. Now it is our choice what do we want. So the literature will tell either you say the d axis voltage is constant and q axis voltage is 0, or you say q axis voltage is constant, d axis voltage you have to make 0. So one of them you have to make 0. So basically then you want to say that voltage is aligned along the other axis. Okay. So here what I have shown is the d axis voltage is the magnitude and q axis voltage we have to make this 0. So you see here now at this point we get the VD and VQ and we compare, just like any any controller, we compare the q axis voltage with the actual voltage. There is error. The error is given to a PI controller. This PI controller generates a signal delta omega and it is added to the nominal frequency. So for example, let's say nominal frequency is 2 pi 50, but you know in a grid frequency it may be variable. Let's 50.1, let's say it may be 49.9, right? So accordingly there is a delta omega signal that is produced here, correct? This delta omega signal is added and you get a new frequency which is called the PLL frequency. This PLL frequency is integrated to get the theta PLL. Theta PLL is fed back to this ABC to DQ conversion here. When you feed back, so this feedback loop works till your VQ becomes equal to your VQ reference 0, correct? So your VQ reference will become 0, you get the required theta. So this is the theta which you use in your ABC to DQ conversion. Okay. Now this theta, keep in mind you have to use the same theta everywhere throughout the system. This becomes your reference angle. This is the angle of the PCC voltage. Okay. So now that angle, this angle is basically, you see you have 3-phase quantities, time varying quantities like this. You can write it in the form of some Vm sin omega t or Vm cos omega t. So then A phase, B phase, C phase. Now, how is the A phase aligned with respect to the D axis? What is the relative phase? Because you know you have 3 phases here and you have 2 D and Q which are like this. What is the relative orientation between these two? So when we align the D axis properly with respect to the A phase axis, that is where we get the desired angle of the reference. So this reference we have to use in all our convergence throughout the control. Should not have different phase angles. Okay. Now once we get the phase angle, we can do the power computation, convergence and everything in all the control. So now we will go into the mathematics of the control. Okay. So let's say you have a distributed energy source and you have to control the power. Okay. Now you know power is, we say in a 3-phase system or a AC system, basically we say power is like P plus JQ, which is nothing but VI conjugate. Okay. So similarly what we do in the, for example, this axis here, we have D and Q. So we can write in the form of VD plus JVQ. Likewise, current we can write as ID plus JIQ. So again we can write S equal to VI conjugate. And if you do the S equal to VI conjugate and you do the computation, multiplication, you get this S equal to VDID plus VQIQ plus J times VQID plus minus VDIQ. So this is basically your P plus JQ. So the real part is your active power, while imaginary part is your reactive power. Now, as I told you, there can be different ways of converting ABC to DQ. You can take phase voltage, line voltage, peak or RMS. Accordingly, what will happen? Accordingly, your factors will come. For example, if you go back to this and you compare these two, root 2 by root 3 or 2 by 3, right? So there is just a factor, just a numerical factor, right? So the d-axis voltage and d-axis current will have a certain, just a factor gain. So sometimes when you see the convert to power, those factors have to be accounted for. Therefore, sometimes you can have these multiplicating factors like this, 3 by 2 VDID plus VQIQ, like that. Okay. So now what we get is, we know how the power is related, okay, to d-axis voltages and d-axis currents, or q-axis voltage and q-axis current. That knowledge, of fundamental knowledge of power, will be required to control the quantities, electrical quantities, when you have a distributed generator connected to the grid through a inverter. So you can have configurations like this. A typical very simple configuration. You can have a distributed energy resource. Now you know, for example, PV output is voltage which is variable. So one case is you get a variable output voltage. So here, for example, the output of this distributed energy resource is variable. Okay. On the other side, you can have a regulated DC source. Regulated DC source means, let's say you have a battery, for example. A battery provides a regulated DC voltage. Or you can also have a PV followed by a boost converter, for example. And the boost converter, let's say, controls the output voltage. So you can have the output voltage as regulated. So you can either have a variable DC voltage, or you can have a regulated DC voltage. Then those variable or regulated DC voltage will be converted to AC using the inverter. And you know, when we use a PWM inverter, we use a LCL filter, and at the output of the LCL filter, we connect to the grid, which is called, this point is called, this bus that you see here is called the point of common coupling, where we connect, right? Now you see here, if this DC voltage is regulated and the output voltage, bus voltage, is also regulated. Why? It is because the output voltage is regulated by the grid, correct? So what happens when you change the current that flows in this circuit like this? Your active or reactive power gets changed. Depending on the magnitude of the current and depending on the phase angle of the current, your active and reactive power gets changed. Okay. So one of your objective could be to control the P and Q, active and reactive power, that is injected into the grid. That is, could be one objective. Another objective could be, in this case, where you don't have a regulated DC source, what will happen? The power flow change will affect this voltage. Why? For example, from the renewable source, let's say you are getting 1 P input, and the output of the inverter is, let's say, P output. What will happen to the difference of this power? The difference of the power, or I can say the difference of the current, will charge or discharge the capacitor. So power indirectly would affect the voltage. All right. So now you have active power, reactive power. You know, the reactive power is the energy carrying thing. So the reactive power will not affect the voltage. So you can have active power which is affecting the DC voltage. All right. So and the reactive power is completely independent. So your control objective can be either of the two. One control objective is to control the DC voltage and reactive power. Other could be to control the active power and reactive power. But the philosophy would remain same, because this DC link voltage is also related to active power only, because the active power change will affect the voltage, correct? So like that, your control objective would be to control the either the DC link voltage and or the active power along with the control of reactive power. How do we do that? As I told you, for example, here, whatever be the case, this is my fixed voltage. If I have to control the P and Q, what I do? We inject a current here. So the controlling of the power, active or reactive power, is basically related to the controlling of the current that is injected by the inverter. So it all boils down to the control of the current now. Okay. So see how we are shifting from one statement to another. Now I am saying that the objective now shifts to the control of the current. Okay. Now, usually what happens when you talk of an inverter, let's say like this. This first LCL filter you have, this first is a first L that is there, this is the main filter. The second one is called a coupling inductance. This is usually smaller in nature. So the drop in this RL pair is very small. Okay. So sometimes for simplicity what we assume that there is no drop in this. Okay. In that case what we can assume that the V bus and VO are same. Okay. So we can assume it just like this. You have R, L and C directly connected to the bus. Alright. Here you have an inverter output voltage V inverter. Now just think about the fundamental component, not the PWM component. Just think about the fundamental component. You can write a equation for this RL pair. Okay. You know the KVL KCL equation for a RL circuit, L di by dt. So we start with that. Okay. Because I am saying the objective is now to control the current. So what we do then, we go to L di by dt. We write the differential equation of the inductor current, the left one. Okay, the filter inductance. Okay, and this here now what we'll see the step-by-step process of actually designing the controller. Okay, so what we have is L di by dt. This L di by dt term in terms of voltage. So you can write simply, right? So you have this voltage V, here you have V inverter, V bus, which is same as VO here. So the difference of the voltage V inverter minus V bus will be nothing but what? Will be equal to L di by dt plus Ri. This is small resistance R. Yes? Yes or no? So simply what you can say, you can write this differential equation. Now takes the Parkes transformation of the differential equation. And that is where the interesting thing comes up. We have discussed so far how to take the Parkes transformation of ABC to DQ like that, right? But transformation of the differential equation. That means you have to take d by dt of all these things. Yes or no? Now what happens if you take d by dt of all these things, this theta, this theta can be written as omega t. Theta is nothing but omega t. Now if you do the differentiation, what will you get? You will get a omega outside. So you will have an omega multiplied term and cos will become sine will become cos with the respective plus minus sign whatever. But the nature would change. So basically you say that the cos will become sine or the sine will become cos. Accordingly you see it is as good as saying that the rows are kind of interchanged. So when you do the differentiation of the transformation, this is where the problem arises. Okay, so you can do this. I am not doing it here because otherwise it will take a lot of time. So I have given the derivation here. Quickly I am going through it. So now what we are doing is we are doing the transformation of the ABC to DQ domain along with the Parkes transformation of the differential equation. So what happens now? Omega terms come up. Okay, and second thing you see here I have written d by dt of IL ABC. That means for the A phase, for the B phase, for the C phase, you have three different differential equations. But here now, as I told, what happens? The rows get changed. So basically for the first row, which is the D, you get the sign terms which are basically related to Q. So not D and Q are interchanged, you get some terms related to D and Q. So now what happens, for the differential equation in the D axis, you get another term which is omega IQ. Here in ABC you don't have this. In ABC you can write VL phase A, IL phase A, IL phase B, IL phase C. Completely three different equations. Here you do not get three different decoupled equation. Because of that differentiation thing, the other terms come up. So now if you see this equation that is there in front of you, if you see, read this equation, d by dt of ILD, the differential equation of the current, carries minus R by L into IL. So that is expected because it will have its own term. But then there is this term also, because if you multiply this matrix, this will get multiplied here, right? So this is what happens now. Your terms get interlinked. So the d-axis differential equation gets a q-axis term, and the q-axis differential equation gets a d-axis term. Now the control becomes difficult. Why? Because, for example, if I have to change A phase current, what I do? I change the A phase voltage. If I have to change the B phase current, I can change the B phase voltage, because they are completely decoupled. Here what happens? Here if you change the, let's say, D phase voltage, it will affect both D phase current and Q phase current. So there is a cross coupling, this is the coupling terms, and the control becomes difficult. That is why now what we developed is called a decoupled DQ axis control. So what we do, we make a rearrangement. What we do, you see this term which is get multiplied, for example, like this, omega ILQ. Omega ILQ, you shift from here and add to this term, okay, and give it a new name UD. Likewise, for the Q axis, you see there is a multiplication of these two quantities. You take it out from this matrix, add to this term, and give it a new name UQ. Okay, so now you see the differential equation. Now you see this differential equation, d by dt of IL, this ILD and ILQ. Now there are no cross coupling terms. Now because this minus R by L will get multiplied by this, and 0 will get multiplied by this, and here the term is UD. So this is the control variable that we want to get from a controller. So what our controller will do, our PI controller will generate this UD term. Likewise, PI controller will generate the UQ term, decoupled term. So now the control is decoupled, we call it decoupled DQ axis control, okay. So the PI controller will generate independent control for D axis and Q axis, while mathematically, you know, mathematically this UD will comprise of, well, these terms, one term coming from here and the term coming from here, yes. So this UD will comprise all these terms, correct, okay. So now what happens, we get these terms we get from the controller. Our controller has to give these UD and UQ variables, okay. And now what we do, we just rearrange this a little bit. You see, at the end of the day, what we want here, we want the current to flow here, as I told, because the PCC voltage is fixed. Because the PCC voltage is fixed, to change the active and reactive power, we have to change the current that is flowing here. How can we change the current? Current would change only when this voltage would change, the fundamental inverter voltage will change. So our objective is now that we have to change the current, and we can change the current by controlling the fundamental inverter voltage. So we have to now know what should be our fundamental inverter voltage, okay. So we have developed this equation that we get from a PI controller, and in this, so UD we get from a PI controller, and you see UD is equal to some terms which contains the inverter terminal voltage. So you can rearrange these things. You can just keep this one on one side and take out others on the other side. So you get these equations. So your inverter voltage reference in the D axis and the Q axis can be obtained by these terms. So while the first term UD and UQ will come from a PI controller, the other terms will come from measurement. Okay? Sorry? So first, when we have rearranged this equation to this equation, I am saying this is the inverter voltage that we need. Because we need, I am calling it a reference and I have put a star. Correct? So now what we do basically, we want that, okay, this much is the VD voltage and this much is the VQ voltage that we want. How will we get it? We will get the UD and UQ terms from the controller, and then we will add this and subtract this, or in the Q axis we will add this. Okay? So the diagram will then look like this. So just forget the left part for time being, just see from here. Just see from here, okay, at this point. Okay? I am saying we need this much current, D axis reference current, Q axis reference current. Compare with the actual D axis current, Q axis current, pass through PI controller. You get the UD term, the PI controller will give you UD and the PI controller will give you UQ. Okay? And then as we have developed this, these terms are there. Just add these terms. Okay? So these terms are added like this. For example, this is the VDO which comes from measurement. Okay? So this is called a feed forward term. It comes from the measurement. Again, if you see, there is another term which is minus omega L IQ. So there is a minus sign, omega L IQ. It goes here. So it's a cross coupling term. Likewise, similarly, you can get for the Q axis. Correct? So like that, by adding the feed forward and the cross coupling terms, we finally get that what should be our inverter output voltage. Like what voltage we need at the terminals of the inverter to get this current. Okay? And now you know inverter voltage depends on your DC voltage and the modulation index. So you multiply by 2 by VDC to get D axis modulation index, Q axis modulation index. And M0 is basically 0. DQ 0, third variable is 0. You convert inverse Sparks transformation using the same theta PLL. What do you get? You get MA, MB, MC. That means you get the 3-phase reference, these quantities. These 3-phase quantities will be compared with your high frequency PWM carrier signal and your PWM will be generated. So I hope you have got the idea that how the control is developed from the differential equations of the current. That we need to have this much current. How we will get that much current? When you know we need to have this much inverter terminal voltage. Now the question comes, how do we know what is the current that we need? Because at the end of the day, our objective is to control the power, P and Q. Correct? So you know the the equation P and Q is given by this. And as we already discussed in the case of a PLL, the VQ term is 0. So if you make VQ 0, this simply becomes like this. S equal to 3 by 2 VDID plus J times minus VDIQ. So you can see P is proportional to ID and Q is inversely proportional to, proportional but with a negative sign, not inversely, sorry, proportional with a negative sign to IQ. So that means depending on what is the active power that you have to transfer and what is the reactive power that you have to transfer, what you can do, you can just find what should be the current that you have to inject. So simply our controller will then look like this. Okay. You can have VD reference minus VD, or you can have P reference minus P. Likewise, Q reference or Q minus Q reference. Go another PI controllers. You get the current reference ILD star and ILQ star. The Q axis current reference and D axis current reference. Okay, simple. So the concept is we have to control the P and the Q. compare with the actual, compare the reference with actual, get the D axis, get Q axis reference currents, compare with the actual currents, goes to the PI controller. The PI controller will give you UD and UQ, the decoupled DQ axis control variable. Then use the feed forward term and the cross coupling terms to get the inverter terminal voltage that you need, right? And that inverter terminal voltage will, if you divide by the VDC term, divide by VDC by 2 or multiply by 2 by VDC, you get what is your MD MQ. Convert to ABC, you get MA MB MC, right? So this is very simple design of a inverter. The problem comes is this: how you tune the controller. So tuning is important. Okay. So when you tune a controller, we have to start from this equation now. Just see this. How do you write this equation? D by dt of ILD equal to minus R by L ILD plus 1 by L UD, right? If I start from this equation, there is no cross coupling or other term. You have two separate equations, right? So this is what we do. We start from this, okay, these two equations, and now you can convert it to the transfer function form, Laplace variable form, differential equation can be formed. So you see, the current relates to the UD control variable like a simple first order transfer function, 1 by Ls plus R, very simple. It becomes so simple, 1 by Ls plus R. Now what I am doing here is I am doing only for the D axis, the same will be for Q axis, okay. So now what happens, you have this this transfer function that relates ILD with UD as 1 by Ls plus R. And how do you get UD? UD is nothing but the output of error multiplied by PI controller. So Kp plus Ki by S, and this input is the error, ILD star minus ILD gives to a PI controller, you get UD. So you can draw it like a transfer function like this: ILD star minus ILD Kp plus Pi by S. The controller gives you UD, and the transfer function is simple 1 by Ls plus R. You get the ILD, you feedback it. So it becomes a very simple feedback transfer function. Straightforward? Yes? Now, very simple approach to tune a PI controller like this, and we use a method which is called a pole placement technique. So you see what happens now. Okay, I have done the derivation for you, so no need to write, you can just see it quickly. So the resultant open loop transfer function, you see here the open loop transfer function is Kp plus Ki by S multiplied by 1 plus Ls plus R, simple open loop transfer function, right? So you have Kp plus Ki by S multiplied by 1 plus Ls plus R. Now I am just doing some rearrangement, okay? So what I am doing is I am writing here is Kp by S, taking S common, like here I have taken out L, so S plus R by L, like that. So this is just a rearrangement thing, okay? So it becomes like this: Kp by Ls into S plus Kpi by Kp into 1 plus S plus R by L, like that. Just a rearrangement, okay? You can just see it. Now you know every first order transfer function like this 1 by Ls plus R, it will have a time constant. It will, step response will look like something like this. Yes or no? So we'll have a transfer function, time constant. Usually for an inverter, because inverter is very fast, we can choose a time constant of our interest like 2 to 4 millisecond. So let's say that time constant is tau. Okay. Now what you do, you put Kp equal to L by tau and put Ki equal to R by tau, and you just put it again in this rearranged form. So you see everything will cancel out, and at the end you will get simple 1 by tau was. So your controller multiplied by this becomes a simple first order transfer function, simple 1 by Ls transfer function, right? Open loop. So if open loop is 1 by Ls with a feedback of just 1, the closed loop becomes 1 upon 1 plus S tau. So you get a very simple first order transfer function between ILD star and ILD. That means as soon as you get a ILD star, after a certain settling time, which can be treated as 3 times the time constant or 5 times the time constant, you know, we get the actual current. So very simple approach. This approach is called a pole placement technique, where we define a time constant and it is usually taken in the range of 2 to 4 milliseconds, and then just put Kp equal to L by tau and Ki equal to R by tau, and you can simply get a very simple transfer function. Now, when we have a control which is like a cascaded control, what we do is, you see here this control that we have developed, there is this controller, here you have the PI controller for the current part, and you have another controller on the outside part. So whenever you have one control connected to the other, which is called a cascaded control, in that cascaded control it is very important that the outer loop should be slow, so that the inner loop settles first. Otherwise what will happen, you will keep on changing the reference before the inner part settles. Yes. Sorry. So when the inner part, when you are designing the inner part, we have already seen how we design. Now when we talk about the outer part, we say that the inner loop is already settled by now. Already settled means what? Whatever is the current reference given, that current is achieved. That means my reference is equal to actual. That means the relation between reference and actual is just a multiplication of gain 1. And therefore, when you design that way, you can make it like this. The reference just a gain 1 becomes your output. Now you see, how do we design the outer loop then? So outer loop is, for example, VD star minus VDC star minus VDC, PI controller gives you ILD star. Now the complete current control loop, now the complete inner loop can be treated like a gain 1, and you get ILD. This is the open loop transfer function. Now you know how a closed loop transfer function works. Somehow you have to get this VDC term to feedback here and subtract. So that depends on your system. For example, if you have a system like this, you have a PV, you have a capacitor, and you have an inverter. So you know, whatever is the PV current minus whatever is the current DC current going, the difference of that current will either charge or discharge the capacitor, and you can write the differential equation of the capacitor voltage, C dV by dt. Very simple. If you can write this differential equation C dV by dt, you need these quantities IPV and IDC. And IDC can be related to ID in terms of power, because AC power and DC power for an inverter are same. We assume, if you assume lossless, so VDC into IDC has to be equal to your 3 by 2 VD into ID, right? VD you know is constant, ID is just obtained here, right? So that means the DC current and ID will just have a gain ratio. Yes. So what happens now? This ILD star with a gain 1 becomes ILD, and another with a gain ratio you get the DC current. And DC current, then there is subtraction with the PV current, 1 by CS, differential equation of the capacitor, you get the DC voltage. This becomes your closed loop transfer function. Correct? Now if you have a closed loop model with you available here, now you see in this type of system, you know, any external signal like this, when we talk in terms of control, this is like a disturbance, right? You remember from the basic control, you have reference, actual, controller, and if there is any other signal, we call it a disturbance. So if we neglect the disturbance for time being, then the control diagram that we have shown can be represented like this. Okay, you have a reference, you have an actual like this, you have a reference, you have an actual, and then this reference and actual error goes to a PI controller. Now this PI controller I have rearranged a little bit. I have taken KPS, so basically common like this, so KP by S common, so here you will get another S in the numerator, so it becomes S plus Z by S, so just the PI controller written in different form. Okay, and then you see you have some transfer function here, you can use it like a 1 gain, or if you still want to do, then remember we discussed that this overall will become like a 1 by tau S plus 1. It can be treated as like a first order transfer function. So if you put this one, the total transfer function between ILD and ILD star. You can put this also here, 1 upon 1 plus S tau. And then I am removing this disturbance term. What I get? 1 by SC. So I get 1 by SC. And you feedback it. Okay? And this K which is there, if there is any other K in K, you can treat it to be a part of this K, because all the gains can be multiplied, right? Yes or no? So basically what we have got it is a transfer function looking of this block diagram looking of something different form. Here the thing is you have two free S in the denominator. When you have such an approach, we use a method of tuning which is called a symmetrical optimum method. Okay. Now what is this symmetrical optimum method? You see, if you see the open loop transfer function from here to here, the open loop transfer function will look like this. And if you make the Bode plot of this, the Bode plot will look like this. Okay. The gain plot and the phase plot. Okay. Now this is your minus 180. Whatever is this available with you, this is my phase reserve. Correct? This reserve will become my phase margin if this frequency where it has this peak, this becomes my gain crossover frequency. Correct? So for example, in this plot that I have shown you, gain crossover is somewhere here, let's say. Correct? If I can shift this a little bit to align my gain crossover frequency at the same frequency where I get this maximum phase reserve, then I can get a maximum phase margin. Right? Because now the term which I am saying as phase reserve would actually become phase margin, and that would be maximum. Anywhere else, if it is your gain crossover frequency, that means you are losing some phase margin. More is the phase margin, stable is the system. Yes? So basically our objective is now to control the margin or the reserve available with us, and to align the maximum phase available at what frequency. That frequency we have to align with the gain crossover frequency. How do we do that? We have these two variables, K and Z. By playing with these we can do it. So you know what happens now if you see the transfer function here. I hope you can agree with me. If you just change the gain K, it will not affect the phase plot. It was just a gain without any angle. Gain K, just the gain K doesn't carry any angle, right? So it will not add or subtract any angle. It will just give a gain. So K will change your gain plot. Accordingly, it will change where it intersects with the 0 dB line. And Z will change your phase reserve. So it will not only change your phase reserve, but it will also change the place where you get the maximum phase reserve. Right? So you can decide what should be the phase reserve available. So the phase reserve available is given by this relation. So you can decide what Z you have to keep to get the required phase reserve. Once you get the required phase reserve, then you can calculate at what frequency you get this maximum phase. Okay, so you get this maximum frequency. Now what you can do, you can play with the gain K to align the gain crossover frequency to match with this maximum phase frequency. So like that you can decide the variable K and you can decide the variable Z, and like that you can tune the outer loops. Clear? So this is the tuning of the outer loop and the inner loop in a grid connected mode when the inverter feeds P and Q to the grid. If you have a 3-phase autonomous inverter, the output will now be basically be the output voltage, because now there is no grid. So your output voltage has to be controlled. Okay. So how do we control now the output voltage? Again, the output voltage is converted to two axis, D and Q axis. we align all the voltage along D axis, we will try to make the Q axis voltage 0. But there is one major difference. The major difference is, in the grid connected mode, we got the theta from the PLL, which is the angle given by the grid, the reference angle given by the grid. Here there is no grid. So how do we get the theta? So theta you generate self, it is self-generated. So what you do, you just get a constant number, okay? You get a constant number 2 pi f, like 2 pi 50, this is your omega. And you integrate it 1 by s, you get theta. That's it. This is the theta we'll use in all the ABC to DQ conversion. So what we get is, the angle is self-generated. The inner loop remains the same, except for a minor difference. I'll tell you. The minor difference, if you see here in this one, in the feed forward term is this, VDO and VDQ. These are the voltages which are controlled by the grid. You see here, this voltage, output voltage is controlled by the grid, assuming this drop is small, correct? So because this is controlled by the grid, we have these terms here. In autonomous mode, we have nothing such thing. No one is controlling these voltages. That's why we kind of remove the feed forward term. That's one small difference. Another difference, I already told you that the angle is self-generated. Third thing is, you have to control the voltage. How will you control the voltage, output voltage? By controlling this voltage across the capacitor, output capacitor, filter capacitor, LCL. And the voltage across the capacitor will have a similar dynamics as the DC link voltage shown here. Yeah, it's similar thing. There is an input current, there is an output current, and the difference will either charge or discharge the capacitor. The same thing will happen here. So there is one current from here, there is the one current which is drawn by the load, and the difference will either charge or discharge the capacitor. So the concept would remain same, right? The only thing is, there we did VDC reference minus VDC. Here what we'll do, VOD reference minus VOD, or VOQ reference minus VOQ. But the overall design would remain same. Alright? Then what you can do, you can write the differential equation of this capacitor just like what you have done for the current here. So here we have written 3 phase. So remember what we have done for DC here, this was DC. Okay, just DC, you can simple write C dV by dt, one equation. But for here we were writing 3 equations because of A, B, C. Now when we are talking about the output voltage control, here it will have 3 voltages A, B, C. So again you will write 3 equations of these capacitor voltage. If you write the 3 equation of these capacitor voltage and you do the ABC to DQ Parks transformation, just like what happened here, you will get this cross coupling terms. Exactly following the same way, you can decide a D axis control variable, Q axis control variable that will have the cross coupling and feed forward terms. And exactly what we have done, the control diagram for the inner loop or the current loop, the similar control diagram can be made for the voltage loop in the autonomous mode. So your voltage is then controlled and your overall control diagram now looks like this. Okay. So you see, you have omega, which is your self-generated nominal frequency, theta. Okay. Then this theta is given to ABC to DQ conversion, VOD star minus VOD, VOQ star minus VOQ, PI controller, it gives you the D and Q axis control variables. Then there is this feed forward term. Now you see the variable would get changed because previously we written the equation was L di by dt. Now we'll write the equation is C dV by dt. So accordingly the variables will change. So in the current loop we have the feed forward as the voltage. Here we have the feed forward as current. And then there we had omega L IQ or ID as the cross coupling. Here we have C omega CV as our cross coupling terms. Okay. The only small difference is the feed forward is not directly given. There is a gain which is called F gain. Ideally, if you give directly feed forward just like the last term, it should be 1. We keep it slightly lesser than 1 for the stability sake only. usually 0.7, 0.8, all of these things. Okay. So this is how your autonomous inverter would work. At the end of the day, just like the grid connected one, what do we get here? We get what should be our D axis inverter reference voltage and Q axis inverter terminal voltage reference. Once we have got that, after that it remains exactly the same as the case of the grid. You multiply by 2 by VDC, get MD, MQ, convert to DQ0 to MABC. So you get the three sinusoidal quantities for PWM generation, and then you have the high frequency carrier. If you resonate the PWM, the inverter will work. The only thing is the theta will come from here. Okay. So this is how the control of an autonomous inverter works. Very much similar to the grid connected one. In both of them you have the outer loop and the inner loop. In both of them you design the controllers such that inner loop is usually designed and the gains are set as per the pole placement technique. The outer loop is designed and the gains are put as per the symmetrical optimum method. So these are the well established method. Okay. Now what we have discussed so far is that the microgrid is having multiple sources. Just a single source will not create an issue. The best example that I give is that, for example, you have an inverter at your home. A home inverter is usually a square wave inverter. It's a completely isolated system. Need not to connect with any other thing. It's quite straightforward kind of thing. So just as you have, if there is a single entity, no need to bother. But if you have multiple things together, then you have to have a coordinated control. You cannot just say, I will do as I like, because there are other people around you. So there are other sources around you. Your control should not affect the stability of the other. So what we have read so far is the basic architecture of a single inverter. But that is not complete. Why? Because we need to have an integration of multiple sources and we need to see how the coordination works between multiple sources connected, and that is the main focus of microgrid. Okay. So the microgrid, as I told, can be a grid connected microgrid or it can be a autonomous microgrid. If it is a grid connected microgrid, you have to take care of some integration issues like synchronization, ramping, islanding, fault ride-throughs, LVRT, those things. So those are integration issues with the grid. Okay. It is an autonomous system. What you have to have is the proper control. So the main issues are the control issues, stability, reliability. The inertia is less because mainly the microgrid have distributed generation which are inverter based sources. So there is less inertia. If there is less inertia, the frequency can change fast. Okay. Renewable energy sources have invariability. So the power management, because let's say if it's a grid connected microgrid and the renewable gets changed. For example, today's date you've seen it's all rainy, right? You can draw power from the grid. But if a microgrid is no grid, then you have to manage the storage and all those things. Okay. So, and the power flow. The microgrid, for example, let's say you have a ring microgrid. The power can flow in either direction, anywhere, any source, any load. So all those control issues are very important and they lead to certain stability issues in the microgrid. Okay. So that all then boils down, how do we control the coordinate the control of the multiple sources in the microgrid. Okay. So before we go into the coordinated control of microgrid, I would then like to touch that why it is important to have a coordinated control in microgrid, because microgrid has got many stability issues. Now you talk about stability issues in a classical power system. The issues are mainly, voltage stability, frequency stability, angle stability. These are the main stability problems that arise in the power system. When you talk about a microgrid, there are other type of stability issues also. And there is one completely other division. When you talk about the voltage stability, frequency stability, angle stability, they are mainly related to the power supply and balance problem. For example, you know, if your generation is more or generation is less in a classical power system, then what will happen? Your system frequency will change, right? If your load is suddenly increased, your frequency will fall. If a line is out, frequency may change due to power balances. Or if there is high reactive power demand, you may have voltage instability issues. True? Okay. That is power or energy balance problem. In the microgrid, we also talk about control system stability, and that is very important. Okay. So let's see this. There is a IEEE Power and Energy Society technical report. You can read this report. It describes in detail how the microgrid stability issues are there. So the microgrid stability can be of two types. One is the power balance, supply and balance stability that we all know, frequency, voltage, and there is control system stability in addition to this. Okay. So the power supply and balance stability relates to voltage stability and frequency stability. Why? Because if there is a large reactive power demand, your voltage stability may get affected. If the active power balance is not there, your frequency stability can get affected. But now in microgrid, the voltage stability can also come in your DC link voltage. Usually we all have AC sources. The voltage that we talk about is the AC voltage. But what happens, for example, let's say you have PV, just like we have shown here, a PV, a DC link inverter. What if there is instability and this voltage falls? The voltage collapse here, right? So there could be DC link voltage stability issues also. Okay. So in a microgrid, you can have voltage stability that can be system voltage stability, and then there could be DC link voltage stability. So all these voltage stability issues can arise due to a small disturbance in the system or large disturbance in the system. So what is the meaning of a small disturbance or large disturbance? A small disturbance, as such, theoretically there is nothing called small or large. It depends on the range of linearity. A small disturbance is what for which we can have a small signal analysis valid. That means linear analysis is valid. For example, that we discuss body plot and all. Okay. So we can have this small variation where the linearity is maintained. We can have a small variation. If the linearity is not maintained, we have to go for non-linear analysis. That is called large disturbance. Okay. If then the stability issues are further divided into two categories: short-term duration and long-term duration. Short-term stability means within the period till your controls are not active. So by the time your controls take action, your what happens? Your system may become unstable. That is short-term stability. Or long-term stability means while your controls are active, if there is a stability issue, they are called long-term stability issues. So the right-hand side part is the power balance issues. Okay. The left-hand side is basically the control system stability issue. That is one important thing that comes when you talk about a microgrid stability. The control system stability can be further divided into electric machine stability or converter stability. Because in a microgrid you will have both inverter based sources as well as rotating machine sources. For example, diesel generator. Diesel generator is basically a synchronous generator. So you can have electric machine stability or you can have converter stability. And then, so basically means the control of the converter or the control of the machine. So that is where the control becomes very important. And that's why in the next module we will discuss the control of the inverter. This can again be classified into either small disturbance or large disturbance. And again it can be classified into short term and long term. So without going into the details, the important thing is the stability is into two categories: control system and the power balance. So how does this stability issue arise in a microgrid? That we will see in the next session that will happen just after this. Okay. Currently we have 5 more minutes now, 5-7 minutes left. So what I'll show you, I'll just stop at this point and You remember this uh, transfer function that I showed you in the body I plot. Just I'll show you how you can get the body plot in MATLAB. Sorry. Where it is? This one, right? So this transfer function, what I have done is I have simulated in MATLAB, okay, and in the tutorial session I will discuss with you how to do the linear analysis. So in the MATLAB there is an analysis where you can plot the body plots, and also let me just quickly show you the body plots. So what I have done is I have put those constant, those time constant k and z, the variables that you saw. Okay, now these are our variables k and z, and this is where I'll plot the body plots. So this is what we got, right? So the gain plot is kind of decreasing, and the phase plot gives you this thing where you have a maximum phase reserve at some frequency. Now what happens if we change the gain? So we change the gain, there will no impact on the phase because just gain k doesn't carry any angle, but it will shift the gain plot. Okay, so let's say I change it to 1. From initially I kept 0.01, I kept it to 1. Okay, so if I change it and I again do the body plot, so you see there is a new gain plot while the phase plot is exactly overlapping. Why? Because we are not changing any phase. Now what happens when you change the gain? You see this is 0 dB point. So the gain crossover frequency would shift. Yes, the gain crossover frequency would shift. Okay. If you change the variable z, let's say from 1 I make it 5 now. Again I plot the body plot. You see what has happened. In the initial part there is some change in the gain plot, it's not much, but you see here then significant change is this. First you see the point where the maximum phase was obtained, it has shifted from this to this, has gone to the right side. That means the variable omega m, the frequency at which the maximum phase is obtained, that has shifted. Okay. Second thing is the maximum phase reserve delta m variable which I discussed, that has also got changed. Okay, so that is how you can see how z affects in this. So if I make the z is small, let's say if I make it 0.1, one more try, you see it has moved to the left side now, the peak has come here and the value has got in between like that. So basically the whole point is by selecting how much is the phase reserve you want, you can select z. That z will define what is your frequency where the maximum phase occurs. Then by playing with the k, so once you have finalized the z accordingly as per your stability requirements, okay, I want this much phase margin, you just put the phase margin, you get z, calculate the max frequency at which the maximum phase occurs. Now that is fixed. Now the only objective left is to align the gain crossover frequency with this frequency where the maximum phase occurs. So for that you can just play with the gain, you can change the gain and you can move it left, right, wherever, so that you can just align with this and change. Okay. Okay. So this is what I conclude here in this session. In the next session we will discuss a little bit of the stability issues of the microgrid, so that you understand why it is important to have a coordinated control between the microgrids, among the microgrid. And then we will discuss the hierarchical control approach of a microgrid, how the control is achieved within a microgrid when you have multiple sources. Okay? Alright. Any questions? If you have any questions, I think we have 5 minutes. So 5 minutes we can just have a question answer and then we can conclude. Ramping issue means, see, when you say, for example, let's say wind is changing or solar is changing, irradiation is changing. That could lead to a sudden power change in the that is going into the grid. Particularly, for example, wind gusts are very high. Okay, sometimes you have a light wind, suddenly you have high wind speed and suddenly low speed. So that variability, what it will do, it will change the power that is being injected, because renewable will extract the maximum power. So that maximum power goes into the grid. The maximum power goes into the grid. What happens? The power that is going into the grid is changing very abruptly. So there is a ramping. The fast ramping up and down of the power can have an effect on the grid stability, because then the grid will see there is power is suddenly changing. So it may lead to some voltage variation, it may lead to some frequency variations, some kind of variation that may lead to issues of the stability. So these are the ramping issues. So ideally we want the power to be, there should be a proper ramp, okay, so that the rate is limited.
Sir, if we switch from AC system to DC system, the switching are reduced.
Sorry?
If we change from AC system to DC system, is the switching are reduced?
Switching are reduced? You're asking this question? Yes. Yeah. So to elaborate my point is, see, if you have, for example, AC generator, the classical power system, and let's say if you connect a microgrid, you have to connect to the AC microgrid. I'm not talking about that case. I'm saying, let's say there's a complete rural area, no grid is there, and you have to develop a microgrid to rural electrify that village, for example. In that case, what will you use? You will start with, for example, a battery, a solar PV. Now, a battery, solar PV, they all produce DC only. Right? Loads that we have, for example, mobile charger and all, they all have batteries. They also DC. What if, yes, voltage are different. So what if we just put a boost converter in between? Right? So the battery boost or the PV boost will charge the home battery or the phone or the laptop or whatever, the appliance basically, right? So that means if your consumption is in DC domain, your generation is in DC domain, because see, nowadays everything is electronics, and electronics works on DC, all your ICs and all, right? For example, your computer, you have SMPS and all, you give different DC voltages. So at the end of the day, you need different DC voltages. Your source is DC. Now, if you convert to AC, for example, even if you use a single phase, let's say H-bridge inverter, you have 4 switches. 3 phase, you have 6 switches. In boost, you have only 1 switch, or maybe 1 switch and diode or like that. So basically what this means, if you know that your source is DC, your consumption is in DC nature, and you have good converters available. Traditionally in a large grid, the problem was that we have to step up the voltage for long distance transmission. Stepping up to a large voltage is possible with the help of transformer only, right? Then with the invention of thyristor and all, that's why we could go for HVDC also. But if you remove that part, when they say stepping up is difficult other than transformer, because transformer works with only AC. But you talk about a rural microgrid, I'm saying, you have to just electrify a small area. You need not to transmit power for a long distance. Then you can work with low voltages, and you can simply use power electronics. For nowadays, we have power electronics for even high voltages, but even for low voltage, you can easily use power electronics. So just by using boost, buck, or bidirectional converter, you can easily manage the power flow. Then definitely it will be cheaper. the main point is generation and consumption both are in the DC domain. So rather than DC to AC and back AC to DC, we just use a DC-DC converter and arrange the power flow. Okay. Any other question? Resistance helps in little bit of damping, as I know. I'm not 100% sure about it, but I think it helps in little bit of damping, and it will have certain internal resistance always. So even if you make a wind a inductor, the coil will have certain resistance. So there is some internal resistance of the filter. It's good to have the filter because it always adds some damping, because it dissipates energy. So, but more is the resistance, more are the losses. So you have to try to keep the resistance minimum to avoid I square R losses, but it adds damping to the system because it dissipates energy. Usually that is the case. It's good to have small resistance for damping purpose. So that's what I'm saying. Internal resistance, parasitic resistance, they are always there. Okay. So those things you can all account for, and at the end of the day, they are all resistance. And those resistance will, I'm saying, will add damping to the system. But definitely, this is parasitic, internal, everything is there. I don't think so, particularly for this system, because when you are talking about PWM delay, PWM works in a scale of some 10 to the power minus 6. That is the order. Here you have a RL circuit. So RL circuit have time constant in the order of milliseconds. So there is a very large time gap in between. So when we talk about the RL time constants, we easily can neglect the time constant of the PWM switching. Although, like if you are studying the device level study, the switching losses and all, then you have to consider the switching dynamics also. But when we are considering from a power system point of view, we are mainly talking about the voltages and currents. So we have a RL time constant with the order of milliseconds. I think those can be neglected. Okay? Alright, can we close here? Okay. Alright then, I suggest we take a 10-15 minutes break, and then we again start for the next session whenever you guys are ready.